The core objective of electrical engineering is achieving absolute measurement precision. Every design, every circuit is built to protect the pure integrity of a signal from the moment it is generated. But there is a universal threat that constantly corrupts that data: electrical noise. In technical terms, noise is any undesirable electrical energy that falls directly within the passband of the signal you are trying to read. This diagram shows the mechanics. The clean signal on the left is combined with interference, random amplitudes and frequencies. The resulting degraded signal shows grassy squiggles superimposed over the true sine wave, masking the real values. Treating all interference as a single monolithic problem is a mistake. To eliminate the noise, engineers must break down the specific taxonomy of how the system is degrading. This diagnostic binary splits electrical noise into two categories. On the right, we have uncorrelated noise. This interference exists completely independent of the signal you are measuring. It is present all the time, regardless of what the instrument is doing. The taxonomy of uncorrelated noise reveals two distinct sources: external forces and internal physics. External factors relentlessly invade from the outside world, including man-made devices, atmospheric storms, and extraterrestrial radiation. Internally, physical materials making up the circuits generate inescapable thermal and shot noise. Imagine a system placed in a perfect vacuum, completely shielded from the universe, and frozen to absolute zero to stop thermal vibration. Even in that impossible isolation, the moment the engineer flips the power on, the signal rating on the screen might still be heavily distorted. Background static is only half the battle. Measurement systems are capable of generating a completely different class of noise just by doing their jobs. The left side of our diagnostic binary is correlated noise. This type of interference follows a strict logic. If there is no signal, there is no noise. This illustrates the trigger mechanism. In state A, the system switch is off. With no signal present, the oscilloscope shows a clean flat line. Moving to state B, the desired signal is pushed through nonlinear amplification, producing the correlated noise that wraps around it. Harmonic distortion is a byproduct of amplification. The circuitry acts as a funhouse mirror, generating distorted copies of the fundamental frequency. Its signature reveals the primary peak F alongside unwanted spikes at exact integer multiples, 2F, 3F, and 4F. Correlated noise is a parasitic distortion generated by the system's own internal processing mechanics. When an engineer looks at a degraded signal, they use this binary to isolate the cause. They test the behavioral relationship between the signal and the noise to see how they interact. The diagnostic test is simple: turn the input signal off. If the primary wave vanishes but static continues, it's uncorrelated noise from the environment or internal physics. But if cutting the signal leaves a perfect flat line, the system's own amplification is the source of the error. Engineers fight a constant battle on two fronts: filtering out the relentless hum of the universe and compensating for the self-sabotaging nature of their own hardware. Achieving absolute measurement precision requires mastering the internal physics of our instruments, ensuring they don't destroy the very signals they are meant to save.